Thank you very much for this very kind introduction. So first of all, I would like to thank the organizers of the symposium inviting me here. I mean, that's really an honor, and I know I'm the last speaker, so you had a very distinguished series of speakers. I hope I can hold up to that level. It's really a pleasure, this visit up to now, so I really enjoy that. So what I want to try to introduce you today is something about what in the atmospheric aerosol community we only discussed since 5-6 years, the discovery that organic aerosols, they have a very peculiar phase state. They can be liquid, solid, and how that affects other processes, atmospheric processes. So that's the aim of the talk. My outline, I will talk a little bit about organic aerosol, then I introduce this peculiar phase state. It's called an amorphous phase state. Then I show you some experiments where we oxidize this organic matter with OH radicals. Then I talk about how this oxidation, dependent on the phase state, changes the hygroscopicity of the particles, so their ability to make clouds. So anyone who is in cloud formation processes will be interested in this. I show you some unpublished data, the first time that we try to oxidize organic matter down to temperatures of minus 60 degrees, very challenging with OH and nitrate radicals. And the last section is a bit, because we don't really understand what's going on here, is how some molecular processes have to be understood if you want to, in a model, predict accurately the chemical evolution of organic aerosol. And there I talk a little bit about adsorption, desorption of species to particles. And then I summarize and conclude. So just a recap that we are on the same page. What is an aerosol? They can be suspensions, multiphase, multi-component in nature, in a gas, liquid, solid, or semi-solid. And the challenge is that they range in orders of magnitude from a few nanometers to 100 micrometers. Makes it very difficult to implement them in models mathematically. Typically, cloud condensation nuclei, which form clouds, are in the range of 50 to 150 nanometers. There are giant CCN, I'm not talking about this. The ice nucleating particles, it's still a bit of mystery. We know that macromolecules can nucleate ice, but it may go up to the tens of micrometers, so they span a bigger area. Just to give you an idea, the diameter of your hair is 70 micrometer, yeah? So what I'm talking about is sometimes 100 to 1,000,000 times smaller than the diameter of your hair, yeah? And it's now a very established fact that if you want to understand aerosol particles, you have to study some organic chemistry, because in every place as we look, there is organic material in the particles. And this is here one study published by Jose Jimenez and co-workers in Science. And everything which is grayish, brownish, and greenish here, these pie charts, doesn't matter if we go rural, urban, polluted, remote, we see there's organic material in these particles. So if we want to predict how they form clouds or what the impact is for air quality, we have to understand this organic matter. And so you know all these pictures. You have this, for example, for air quality motivated research, these smog clouds in big cities. Yeah? And we have that in New York, in LA, and likely in Mexico City. So how do they look like? So my first single particle view was I got samples from the Milagro campaign from Mexico City years ago. And that is an electron microscope picture. And what you see here is solid, inorganic, organic inclusions. And this gray shadow here, this is secondary organic material. This is like organic gooey, yeah, that forms from in the gas phase and condenses, for example, on the particles. We call that secondary organic aerosol. Here sampled, and we showed that this organic material can nucleate ice, and it took a few years for the community to accept that for the maturity. As we sampled particles nearby an incinerator, we have different shapes of particles because we have some heavy metals involved. And here these are particle samples in Los Angeles, and what you see is very similar. We have inclusions, blackish, these points inorganic or organic, and we have these gray shadows engulfed in this secondary organic matter. Yeah? Biomass burning, there's a nice review article by Laskin and co-workers. There is a particular particle called tar balls. We don't completely understand them right now. They are highly carbonaceous, solid-like glass marbles. They don't evaporate if you heat them up to 600-700 degrees Celsius. We don't really know what that is, but they are very ubiquitous in forest fires. And if you see the size, they can be transported, and maybe they interact with cloud formation. Here, sea spray aerosol we sampled in Long Island on the South Shore, in the surf zones, in the Hamptons, where all the rich people live. It's unpublished, so we could go with our state truck on their property and measure. There's no access for the public usually. And what you see is this is an X-ray microscope image done at a synchrotron light source in Lawrence Berkeley National Lab. You see beautiful cubic salt crystal, sodium chloride, and engulfed in organic matter from the ocean sea surface. This here is an sea salt particle we collected in Central California. The organic, if it's carboxylic groups, there can react with the chlorine, expels chlorine, and then you get a dendritic inorganic structure. You have here a calcium spine and organic around it. So although there we have organic material. The Laskin group recently pushed a few new paradigms. They collected organic particles in the Amazon, and these are fungal spores, rather large. But if the humidity increases, they explode. And they eject many small particles, but also salt particles. And in principle, every cell has salt water in it, or we have not water in the cells. And what they suggest is that the salt particles we detect always in the Amazon are not coming from transport from the Atlantic Ocean. They are maybe plant-derived or fungal spore-derived. They also came up with a new particle, and they call it airborne soil organic particle, ASOP. And what they found is that after a rain event, if a droplet falls on soil, the organic matter promptly dissolves in the water, instantaneously, the dissolvable material. You have bubble bursting as in the ocean surface, and it ejects hundreds and thousands of very small organic particles. And if you collect them on an impactor, they look like this. And that means as they impact with high speed, if they are liquid, they make these pancakes. If you have sulfuric acid droplet or so. But if they are solid, they're like glass marbles. And they're everywhere around. Every time it rains on soil, on agricultural fields, you have millions of these particles generated. We have not yet accounted for them. So there is ongoing research. What are the properties of those? Of course, aerosols have a big impact not only on the air quality but on climate. And I guess in this audience I don't need really to explain this figure from the IPCC showing the change in radiative forcing from present time to pre-industrial time. That's a very complicated plot. I cannot completely explain everything, but as you know, you have different atmospheric constituents or processes, and we look at the change in the radiative forcing, where positive radiative forcing is associated with the warming of our troposphere. And the point here is that some of the large uncertainty bars are related to aerosol processes. And so, for example, and I show here only one example, if you have an unperturbed cloud with a given liquid water content, you have aerosol particles which form this cloud, and now you add more aerosol particles or more hygroscopic, so water-loving aerosol particles, then you distribute the same amount of water to more particles, like sharing a bottle of water with more people. So the aerosols, the droplets are smaller, more numerous, and that usually results in higher reflectivity or precipitation suppression, etc., and has a climatic impact. So we are interested, what are these roles of aerosols? So here now we come and we see here the first mention of this amorphous phase states. There's a nice overview article by Shiraiwa et al. So if we have organic aerosols, primary emitted or secondary formed, they could be solid, semi-solid, or liquid. And I go through that in the next slides. But what it means, as soon they're in the atmosphere, they're bombarded by oxidants. They react chemically, and they may react in different ways at the surface or in the bulk, depending on the phase state, and that will in turn affect cloud formation processes. And so what you usually learn in the textbook, if we have salts, the phase transition of salts is instantaneous. And what I mean with that, and you can try that at home, if you have a salt crystal, and here's the humidity, and that's just the change in size, you increase the humidity and instantaneously it becomes liquid at a certain relative humidity, and then it grows to a cloud droplet. And if you put the cloud droplet into drier conditions, it instantaneously crystallizes and becomes solid. Yeah? And that's how most salts behave. However, these amorphous organic materials, they do that in a continuous way, and it all depends on thermodynamic conditions. And so what is given here is different phases. We all know water, olive oil, honey, and we call that liquid because it flows. Yeah? But then if you look at ketchup or peanut butter, clearly peanut butter is not a solid. But if you put your bread upside down, it doesn't drop off. And so we call that semi-solid. By definition, you have your viscosity parameters. It's the same as your car. If your car is at minus 20 degrees, you need a different engine oil to keep the viscosity low. If the viscosity high, your car doesn't start anymore. And then here at this range we have a solid material, glass marble. Yeah? So glass windows are not crystalline, they flow, but they flow very slowly. And that is what we see with secondary organic aerosol. And the point here is that it depends strongly on temperature. As you get colder, usually you get more solid-like. If you increase relative humidity, you can maybe, depending on the hygroscopicity of this material, make them liquid again, but it all takes also time. So it's not something instantaneous. So even if you expose them to high relative humidity, it may take half an hour till it is completely deliquesced. And that depends on the chemical composition of that material. And that is where a lot of people do investigation. So for the modelers, all that is in principle given in relation to the updraft velocity. How quickly does it go up? And what is the phase state as it goes up for cloud formation process? It gets really complex, as a matter of fact. And so if you have this scale, you have a diffusion coefficient, meaning, okay, in a liquid, how long does it take for a 100 nanometer particle, given here, how long does it take to transport a molecule through this 100 nanometers? If it is glassy, you can use here Stokes-Einstein equation, it can take 10 years. So under atmospheric lifetimes, it will never mix this particle. That means you will never access the core in the particle. You can never chemically modify it once it's in the glass phase. But if the same chemical, the same particle is liquid-like, it goes in milliseconds, microseconds. Yeah, and we do not yet account for that in atmospheric chemistry models. So that's really very new insights. And so what we also know is if we start mixing these chemicals, we can change when this particle becomes solid. So for example, what I plotted here is the temperature in Kelvin, 300 Kelvin. If I take glucose, a sugar, or levoglucosane, that's a biomass burning marker, above 300 they are liquid or semi-solid. And if I cool them below, they are solid. But if I mix, and now look here at the black one and blue one, if I mix sulfates in it, sulfuric acid, I can dramatically change the point when these particles become solid or liquid. Yeah, and that means if a biomass burning plume comes over Mexico, takes up sulfates, the thermodynamic conditions when the phases changes. Very complex. Yeah? And there are beautiful experiments, Sauco et al., what they did bounce experiments. And what they said is they take a substrate, and if a particle is solid, it impinges and bounces off. And then they know it's solid. But if it's liquid, it impinges, makes a pancake, and never comes off. And so they did that with solid particles, but then they used a secondary organic aerosol, and they added sulfate. And so if you have 28% of sulfates in it, as you increase the humidity, you see less and less particles bounce off. They become more liquid-like. Yeah? And that changes their reactivity. It changes their interaction with cloud formation. Oops. And if you increase it to 36% in this experiment, they're always liquid. Yes?
Can you speak a bit slower?
Slower? All right. So, okay. I will try. So, depending on the composition, the sulfate, this is now a bit awkward, you know. But the sulfate will make the particles softer, yeah? And if they are softer, the phase changes. And here's a very beautiful paper by Shiraiva and co-workers, and they try to estimate what is the phase of secondary organic aerosol as a function of height, and red means they're solid. They go close to the surface, and from the knowledge of the chemical composition of the particles, they see there are regions where they are solid, a particular dry region, but just if you go a kilometer up or two, you get a vast amount of solid glassy particles, and 500 hectopascal, 5 kilometers in height, they say all SOA is solid, glassy. Okay, and then they come up with the same picture. SOA starts liquid, and as it goes up, it becomes solid-like, and it will affect chemical transformation, ice nucleation, cloud formation. Yeah? Okay, so what do I understand as the multiphase chemical kinetics? So what do we measure in the laboratory? And we look at radicals, for example, OH, NO3, which make it to a surface, and at the surface it can adsorb or desorb, or they stick at the surface via a mass accommodation coefficient. And then they can react at the surface, they can dissolve, Henry's law constant, and react inside, and then products could be expelled to the gas phase. And so what we measure classically from polar stratospheric cloud folks, Hansen and Ravi Shankara, it's the same methods. We measure something called the reactive uptake coefficient. Means the number of particles that collide and which are lost by reaction. It's a value between 0 and 1, meaning 1 means it collides and it reacts, it's gone. Okay? And that is what we measure in the laboratory to establish the kinetics. And how do we do that? We have a home-built chemical ionization mass spectrometer. It's a quadrupole which detects the ions. We have soft ionization, we have a charge transfer, SF6- to OH, and we can in situ detect OH as OH-. And that looks like this, so it's a big machine, huge turbo pumps, we have high flows, especially for OH radicals because their lifetime is so short, and a differentially pumped system. The science happens in these flow reactors, where we have, in this case, organic substrate on the surface, on a cylinder, and then we inject OH via a movable injector here, and that looks a little bit like this. It's the top view. They're different in size. Sometimes they're rectangular. So depending on what we look, these reactors look a little bit different. So they're tubes, and we do it at low pressure to avoid any diffusion effects. We make OH by having a hydrogen plasma with a microwave cavity. That's really old school atmospheric chemistry. Ferguson, Molina, Sherwood did this in the 70s. And then the H reacts to completion to 2OH. And it's very clean source. No other chemicals are involved. And so what we do conceptually, it's a very simple experiment. We expose the organic surface to OH coming out of the injector, and we pull back the injector. And every time we pull back, we have more reactive surface. So we lose more and more OH if it reacts. And if we do that, and the experiment works, then you have this stepwise decrease in OH concentration. If we push the injector back beyond, the concentration goes up. And from this, we can derive this nice pseudo-first order heterogeneous kinetics. So it's not like gas chemistry, OH reacts with methane. It is truly the reaction rate between OH and the substrate, heterogeneous or multiphase kinetics. And the steeper the slope, the faster is the reaction. And so we did this. We were then interested, okay, we know now the organic change's phase. How does a phase change affect this kinetics? And so we used aerosol particles in this experiment, and we measured the reactive uptake coefficient for levoglucosane as a biomass burning surrogate material, and we did it under dry conditions. So it's solid, it's glassy, and the reactivity is something 0.2. So every 2 out of 10 OH reacts, and then we humidified them up to 40%. We could not do more than 40. It doesn't work with the experiment. And we see almost a 3-fold increase in reactivity. And so our suggestion was, and the Murray group in Leeds, they published diffusion coefficients of water in levoglucosan, and we thought, okay, that these lines here, maybe this material becomes softer. Because it's softer, OH can go deeper in and react more, and so the reactivity increases. And we published that in GRL, but that's wrong. And I show that in the next slide. A different organic material, also in biomass burning, that's methyl nitrocadmiol, complicated molecule. It's not really of importance now, but it's solid too. But then we increase water, and we see the opposite. The reactivity goes down. Two organic particles, complete opposite behavior in a biomass burning plume, idealistically speaking. And what happens here is that OH and water vapor, they compete for sites on the particle, and there's much more water vapor than OH, and the water vapor covers the organic and produces like a protective shield. And that is an agreement, if we go into the water adsorption theory, with previous studies by Uli Pöschl at the Max Planck Institute for Chemistry in Mainz. And so, one hand, we increase reactivity, so the lifetime is threefold shorter for this material. And here we have protection by water, adsorption. So to understand that a little bit better, we collaborated with the folks at the Max Planck Institute for Chemistry in Mainz, and they have a very detailed multiphase chemical model. And I'm not going much in detail here, but they can describe the movement of gases to the surface. They treat desorption, adsorption, reaction on the surface, reaction inside that runs on a Linux cluster. It's computationally demanding, but you can put all these molecular processes in to come up with parameterization for larger scale models. And so we did this. We modeled or simulated our red data here. This is the uptake as a function of OH concentration. So in the atmosphere, the OH concentration is somewhere here. But most experiments in the literature are done down here at 10 to the 10. So we are not doing most kinetic studies with OH at truly OH concentrations. And what you see is, what we found or observed is, as the OH concentration goes up, the reactivity goes down. And so we try to understand, why is the reactivity going down? Because that would infect everything. All the chamber experiment flow reactors for SOA yields has a lot of impact, that because everyone assumes the uptake is between 0.1 and 1. And that is maybe like that in the atmosphere, but in many experiments not. And so we model this, and what we see here as a function of time is, is within microseconds we have mass transfer to the surface. So that's a standard equation for droplet growth or so, that's textbook. But what happens then for low concentration, like in the atmosphere, only reaction on the surface happens for very long time scales. However, if you increase the OH concentration, you suddenly see that the reactivity drops off. And there's something called bulk diffusion. So what is happening? And usually chemists, if they see that, they think, oh, OH goes to the surface, saturates the surface, and then reactivity slows down. And that is how we published that. But that's not quite right. So if we look, what the model suggests is the following. After 100 seconds, that is a concentration profile of levoglucosan, and that is from the surface inside the particle or substrate, 5 nanometers. And so about 100 seconds, you see depletion of levoglucosan on the surface. So the OH reacted it away, it degraded it. But there's a huge gradient inside, meaning there is a big concentration gradient, and so no fresh levoglucosan can make it to the surface because it's glassy. The movement of the molecules is too slow compared to the chemical oxidation occurring on the surface. If you look at OH concentration profile, it only goes 1 nanometer in. That's contrary to any textbook knowledge. And it only accumulates exactly when we the depletion have here on the surface, but the concentrations are way too low. There's no saturation effect. Meaning the picture is completely different, and Barbara Finlayson-Pitts is following a similar concept, that You oxidize the surface and the reactivity slows down because you are diffusion limited, bringing unoxidized fresh material from the bulk of the particle up to the surface. And that slows down the reactivity, and that's in contrary to any physical chemistry textbook. So it's a different mechanism, and that is in the moment ongoing research. And you will hear this theme again. Of course, that affects if we want to study source apportionment, emission strengths, air quality related aspects or lifetimes of this material. So here I plotted the half-life of a 200 nanometer particle as a function of OH concentration, and if it's in the cloud, it's aqueous, so it's liquid. So it can diffuse everywhere, has a huge exchange. Lifetimes are pretty short, like what we often estimate a day to a week. As soon as it is dry, you gain maybe almost a factor of 10, and then you see there's a temperature effect. As you go up in the atmosphere and the particles become glassy, the lifetime can be years against OH oxidation. And that, in fact, explains some funny findings. Dan Murphy from NOAA always told me he finds this organic material accumulated in the upper troposphere, lower stratosphere. And OH concentrations are higher there. And he estimated lifetimes over 3 months. And how can all this organic material be there? It must be all chewed up by these chemical reactions. And so the idea is what happens, the OH chews up the first monolayers of organic material, but no fresh material from the bulk makes it to the surface. It just slows down, and it stays there forever, in quotes, until you have a loss by wet deposition or dry deposition. That we can use these detailed studies for chemistry models. We tried an attempt here in 2011 with Nicole Riemer. We used an urban plume box model, RADAM2, and we put a particle resolved model on top of that to see how would this chemical kinetics affect atmospheric composition in an urban environment. And we studied PAH-coded soot particles, and we looked at the degradation of PAH on soot particles, which is a common pollutant in cities. And we have here the diurnal cycle, 6 o'clock in the morning, 6 p.m., midnight, 6 o'clock in the morning. And we have a highly polluted megacity. We modeled here ozone, nitrate radicals. So that's just an idealistic, just to show, model how to use our laboratory data in this context. And we plotted here the half-life of PAH on soot with respect to purple OH. Bluish here is nitrate radical, and red is ozone. So the smaller that is, the more dominant is it in degrading the PAH. And what you see, contrary to textbook, which says OH is the strongest radical and it will degrade everything, no, in an urban environment, during the day, ozone wins because it's orders of magnitude more abundant. So even so, the chemical reactivity of ozone is much slower than OH because it's up to 6 orders of magnitude more abundant. It compensates the lack in reactivity. And therefore, ozone wins during the day and determines the lifetime of pH. And during night, there's not much OH, so it doesn't do anything. The nitrate radical determines completely the degradation of PAH in this idealized model. Yeah, I'm not claiming that's the real world, but we just wanted to show how you can use that and then account for humidity, for diurnal cycles, if you have this detailed molecular insight. And it is challenging mathematically to implement that, and we have not yet continued with this research. My second topic, how does that affect cloud formation? And so what we did here is we looked at fulvic acid organic particles as a surrogate for biomass burning again. And we produced them, dried them, and put them in an aerosol flow reactor. And I'm not saying here much, but it's at 1 atmosphere. We have to make the OH a little bit different. We expose it to OH. We do it like in the atmosphere. So ozone is in there. The ozone is split. Atomic oxygen reacts with water vapor, and you get OH. We oxidize them here. We can do that temperature controlled. And then we dry them, we look at the size of the particles, if it changed or not, the size distribution, and then in collaboration with colleagues at Brookhaven National Laboratory, we run here a cloud condensation nuclei counter. That's just simulating cloud formation, and we get the particle hygroscopicity out of this measurement. We can adjust the supersaturation and see if these particles would form a cloud under atmospheric conditions. And why did we take fulvic acid? Because in a previous ice nucleation study we did a few years ago, we determined the glass transition temperature of this material for a wide range of relative humidity and temperature. So we know above the solid line, the particles are like ketchup, peanut, or liquid, and below they are solid, glassy. And we know that, we saw that, we measured that. So we said we do our experiment where the particles are semi-solid, and then we cool down and do the same exposure experiment at cold temperatures. All the same chemistry, same particles, same OH concentration. Will there be a difference in the ability to form clouds? Yeah? And so what we see is plotted here. Here's temperature. Red means they are liquid. Blue means they're cold. And on the x-axis, we have OH exposure. And you can think about that as 7 to 10 days in the atmosphere. Okay? If they are liquid and we bombard them with OH and oxidize them, there's almost no increase in particle hygroscopicity. And here I forgot to mention that is kappa. And I'm not going much in detail. The larger the number, the more hygroscopic it is, the easier it can take up water and form a cloud droplet. Yeah? And there's no change really, and fulvic acid is slightly hygroscopic, doesn't do anything. But if the particles are cold, solid, and we oxidize them, we see almost a threefold increase in hygroscopicity. And why is that? Same chemistry, same material, everything the same, except these are solid, they are liquid. And I have a cartoon to explain that. It gets a bit complicated. What is happening is, here's temperature, particles are liquid, here they are solid. This is again hygroscopicity, so it jumps up here when we expose them to a lot of OH, reddish. And so Jesse Kroll's group at MIT years ago showed that if OH reacts with fulvic acid, you fragment some of the molecules, but not all, a few. They did it in liquid at high temperatures. And if you fragment molecules in an organic particle, your hygroscopicity increases. That comes out of the theory, and I don't bother you with that, but you can look at that. If you change the molecular weight, hygroscopicity increases, everything else stays the same. And if we do this, we only get a marginal increase. So what we suggest, we have much more molecular fragmentation somehow if we have a solid particle, and that shoots up the CCN ability of this aerosol. And how can we think about that? So imagine you have a liquid particle, and brownish are our fulvic acid molecules, and here's OH coming, and it diffuses to the particle, attacks it, and a single oxidation step is classical, gas phase chemistry. It oxidizes, takes the hydrogen away, makes an alcohol, peroxy radical, etc. Okay, but it's liquid, so the molecules move the whole time. So within nanoseconds, the oxidized particle goes in the bulk and it's gone. And the OH comes again and oxidizes the particles on the interface, and they're gone, and it oxidizes again on the surface, meaning many of these particles get singly oxidized. They're from alcohols, carboxylic acid groups, and that's it. But what is with a solid? Yeah, same picture. The one on the interface will be oxidized, but they cannot escape. Yeah, the time scale is years to go inside or from inside out. So they stay there. OH comes, reacts the whole surface, and so now we get what is called in atmospheric chemistry multiple generations of oxidation. The same molecule is bombarded several times with OH. And we know from chemistry what happens is then it fragments the molecules. And that's standard knowledge in organic chemistry. So what happens, I try to picture that here, the molecules become smaller. They're highly oxidized. The O to C oxidation ratio changes dramatically. We have CC bond scission. We got a ton of fragmented molecules. And we believe that is our hypothesis. That increases the hygroscopicity. And that's something has not been considered. The point is, most atmospheric chemists do everything at room temperature. But we all know the average temperature in the troposphere is much colder. Yeah? So that means maybe we are missing here out something. And that it has really an effect on cloud droplet numbers. We do that with a sensitivity model from the folks at the Max Planck Institute of Chemistry in Mainz. It's a beautiful cloud parcel modeling study if you want to know how cloud droplet numbers change as a function of this hygroscopicity. And that is in black, the numbers, and then saturation in red. And what you see is, for many different cloud types, most sensitive changes are between 0 and 0.1. Meaning, if you have a cloud and you have a particle with a hygroscopicity of 0.3 and you add particles with 0.4, you don't change the cloud much anymore. The biggest sensitivity is here, and that's exactly what happens with our background oxidation of OH. It goes from 0 to 0.8. We are exactly in this range. Yeah? And so what we did is we simulated Hang Su from MPI for chemistry, ran his model, this model again, for typical biomass burning plume conditions with a log normal aerosol size distribution for different particle numbers, for different updraft speeds. And what you see, fulvic acid unoxidized versus a week in the atmosphere, you see an increase in these, it's all idealized, yeah? I'm not claiming that's the real world, but you see increases from 5 to 25% in cloud droplet numbers because of this slight increase in hygroscopicity. Now you could argue is not a lot, or 5%, 25%, but if you take that and do back of the envelope calculation and look at the reflectivity of clouds and then the reflectivity of planetary albedo, it counteracts CO2 warming. Okay? I'm not just saying that, don't quote me on this, it's of course not realistic, just to say that this little effect, it looks minor, may be something we should look at, and people start doing that now. And so that's the classical TUMI. So we have the ship tracks in the natural marine steroidocumulus because we have more aerosols which are more hygroscopic, yeah? And that's the same effect. I promised Louis not to talk about ice nucleation, but I have to show this figure from our recent review because I think it will affect ice nucleation dramatically, this concept. And I do that very quick. If you have an amorphous glassy aerosol here, and you increase relative humidity as the particle moves up, what happens is here you are solid, and if you are purely solid, you have a different nucleation pathway for ice. Then it starts partially to deliquesce, but it takes time. It doesn't happen instantaneously. It may spread over 2 kilometers, depending on your updraft. So suddenly you have an aqueous solution in a solid core, so you have immersion freezing, and then at a certain point it's completely liquid, and if it's not cold enough, it will never freeze. Or it freezes homogeneously if you're below minus 35 degrees Celsius. And this is a very complex matter, and I said here, who wins the race? Does ice nucleation win before the particle is deliquesced? So suddenly things get a little bit more complicated, yeah? And I'm just putting that out here. So we did low temperature studies of uptake down to minus 60 degrees in our flow reactor, and we realized one of the most challenging things are, how do you know that your substrate is glassy? You know, you put it in, cool it down, and you hope it's solid or glassy. What is it? And what we used here, we struggled a lot with this, and the Murray and Bertram groups, they came up with this poking needle experiment, meaning you stick your finger in your glass and you pull it out, and then the surface is flat again because it's liquid. Yeah? And so you can do that with a microscope, and you look at these substrates, and if they reform quickly, you know they are somehow liquid-like. But if they're glassy, they shatter. Yeah, that's pure, that is, I think, levoglucosane or glucose. They really shatter like glass, and they stay there forever, for hours, because it's glassy. And so we have a qualitative control of the phase state of our substrates. And then we rebuild our whole heterogeneous experiment, and it's almost going back in time to polar stratospheric clouds. So how do you cool this whole thing down to minus 60 degrees? And we validated this experiment, and there was not much low temperature studies involving organic aerosol. De Gauw et al. They measured canola oil which you put in salad or in food, reaction with ozone, and these are the solid, there's these diamonds, and as it solidifies at minus 11 degrees, the reactivity goes down 1 to 2 orders of magnitude. And so we reproduced that, and so we are pretty confident that our experiment, and we extended it to minus 60 degrees, that it works. Here's a funny thing. There's 40 degrees difference, and the reactivity only slightly changes, and I don't understand that, because if you think about Arrhenius, 40 Kelvin difference, reactivity should slow pretty much down. That's something we don't understand, and maybe here adsorption, desorption is a key factor, and I say something in the last 5 minutes to that. So what we did is NO3 radical uptake down to minus 60 degrees on levoglucosane for biomass burning aerosol. What you see here within the uncertainty, nothing really changed. The glass transition of levoglucosane is about 10 degrees. And so what we think, looking at the substrates, at 20 degrees, minus 60, morphology is very similar. We think it's still highly viscous. So it's in principle a very similar phase state. And so we are not sensitive with our instrument to see changes in uptake kinetics. However, if we now mix into it xylitol, something with a lower glass transition point, so we can change the phase transition, and theory predict it should change at minus 10 now, not at 10 degrees, and we do the same experiment again. So we have an uptake of about 10 to the minus 3 at room temperature, and then at minus 10, you see it really goes down by a factor of 3, meaning just 1 or 2 kilometers higher in the atmosphere, the lifetime against NO3 degradation is a factor of 3 longer. So if it was 3 to 6 days before, now we talk about several weeks. And that is very important for source apportionment, estimating of source strengths. We do everything at room temperature in atmospheric chemistry, most, not ice nucleation. So Lewis is one who goes to low temperatures. But that is really, I wanted to point that out. That is our recent one, last result, still unpublished. This figure took us 1 year full time in the lab. And you cannot just publish one figure, unfortunately. But this is OH uptake, biamorphous glucose down to minus 40 degrees. And what you see, as soon the particles are transported up, in the boundary layer, it's liquid. You have a reactivity close to 0.1. And then in the mid-troposphere, it decreases by almost a factor of 2. And that also goes in hand what I said in the beginning. The lifetime of this organic aerosol will be much, much longer. Okay, my last topic here, 5 to 10 minutes, I hope I'm in time somehow, 5 minutes, okay, is to understand that better on a molecular level. The first step, multiphase chemistry, what happens? A gas species adsorbs to the surface. And if it doesn't stick there long enough, it promptly desorbs. It's not important, nothing happens. But what we know is if the temperature goes down, it can stick much longer there, and it may undergo reactions which you do not observe under room temperature. Because under room temperature, the thermal energy is so high, it goes and goes off. But the troposphere is not room temperature. And so with Markus Ammann at Paul Scherrer Institute, Uli Pöschl, director of Max Planck, and Manabu Shiraiwa, we try to, since over 2 years, write this paper, a perspective, to figure out how important that is. And so we focus on desorption lifetime. So how long does a species stick on a particle? And what you see is 1 million seconds, 10 to the minus 12 seconds, 18 orders of magnitude. And that depends on the adsorption energy. The higher the energy, the stronger the molecule stays on the surface. A bigger molecule stays longer on the surface than a small one. And if you start putting the temperature dependence here, what you see, at laboratory conditions, maybe a millisecond, microsecond. If it doesn't react in that time, not important. But if we go to lower temperatures, we gain orders of magnitude of lifetime. So it can change completely the chemical reaction pathways, what is really going on in the majority of the atmosphere. And so we want to try to emphasize that in this paper, and just maybe one or two figures, then I'm done. What we did here, we used this model I showed you before for our OH experiments, and it's an idealized OH uptake on a solid. And what we say is, okay, and we say the reaction rate, we give everything, we just change the desorption lifetime. If we do it at room temperature, we get an uptake coefficient of 0.02. Just at 0 degrees, it increases by a factor of 3, just because the radical stays longer at the interface. Yeah? And so we would completely wrongly, in a model, extrapolate that. In the model, we just use the room temperature measured uptake coefficients in global chemistry models. Yeah? If the molecule sticks stronger by its absorption energy on the surface, then this effect is much minor. So we have to know what is this absorption energy and translate that in our kinetics interpretation for chemistry models to predict the chemical evolution of that material more precisely. Because we talk about a factor of 3, meaning if it degrades in 2 days, it doesn't make it over the Pacific, affects not the Americas. If it's a week, you will measure it in California, for example, if that material is in the Asian haze. Yeah? So that is, in principle, the bigger picture. And now I don't know if I don't have time. We did this for liquid particles too, and the idea is SOA formation. The whole SOA formation idea is it happens in the boundary layer. The organic aerosols are liquid, although they could be also solid. And here we have also strong temperature effects when the condensing organics have a high adsorption energy. And these are huge molecules. They usually have high adsorption energies. And what you see is that this is equilibrium timescale. That is, when is a particle in equilibrium with the gas phase? And we have big differences between room temperature and lower temperatures. And again, we do everything, our chamber studying everything at room temperature. So soon it lifts upward and still forms or condenses VOCs. Timescales will be very different. And that has to do because desorption lifetime scales different with temperature than Henry's law constant. Okay, my last slide, bear with me. So I summarize and conclude. So first of all, I want to make clear, if you want to understand aerosols, you have to study a little bit organic chemistry, because there's a lot of organic material, and I had to do that. And Alan Bertram forced me in UBC to become an organic chemist, and it was good exercise. But what my point is that this organic phase state is modulated by RH and temperature. And that then modulates how the reactivity of the particles, it modulates the lifetime, and it impacts air quality, source apportionment, etc. And so that is something people start considering now. I showed you that everything the same, but the organic is solid, and then it's liquid, we get different particle hygroscopicity. And clouds do not form at 20 degrees Celsius. They form higher up, it is colder. Is that something we have to consider or not? Is it important or not? We don't know yet. And what is very interesting is if you go to remote regions like the Amazon and you look at the hygroscopicity of the particles there, they're all around 0.1. Even the global models show that, and no one knows why. So if you have very little sulfates, and so maybe this background oxidation of organic material, what I showed you, which enhances it towards 0.1, maybe that is the cause why all these organic particles end up with a hygroscopicity of 0.1. Climate modeling is interesting. Everyone asks, what is the CCN activity pre-industrial? No sulfate in the particles, versus sulfates. Now you add sulfates because of our activities, the particles become more liquid. But pre-industrial, maybe the particles were all more glassy. And these are questions the community discusses. And lastly, to fundamentally understand that, yes, we think the desorption lifetime deserves a little bit more attention. And so we try to summarize these ideas and put that out maybe till the end of this year. And that helps to extrapolate these findings in atmospheric chemistry models. Okay, with that, I thank you, of course, for your attention, and I thank DOE for funding our phase transition ice nucleation studies. We got funding from the National Science Foundation for the multiphase chemical kinetics studies. The data you have seen is mostly from Jonathan Slade, who just accepted a faculty position, University of California, San Diego, with Kim Praser and these folks. Jinan Lee and Shona Forrester are current students, and then my national, international collaborators. And I thank you for your attention.
Thank you, Daniel. So is there any question for Daniel? So there is one here.
Oh, well, thank you. So it is very surprising to see some of the ideas that you have shown. So if you talk about lifetimes, the sorption lifetime, it means some kinetics.
Yes.
In it. So the idea of instant transfer in the aerosol chimps CO formation have to be rethinking?
Yes, so in fact, often for simplification reasons, you assume instantaneous mixing or so. But in fact, and it started with you know, the ozone depletion, so the compounds like inactive reservoir species absorbing at PSCs and then reacting to active ones. Since then, we know that this process, in fact, is several steps. Yeah? So you have resistance due to gas diffusion, you have resistance on the interface, that making across the interface, then you have bulk diffusion, and then you have reaction. So if you want to do it on a molecular level, yes, the instantaneous mixing is very simplified. Yeah? And my point is, if you simplify it, you will not catch the effect that the kinetics may change, even diurnally and all that. You have then, for example, if you look at Daniel Jacobs' atmospheric model to get the NOx and OH budget right globally, they put one fixed reactive uptake coefficient in it and say instantaneous mixing. But in fact, what happens is then, depending on the concentration, and what we add is depending on the phase, these reactive uptake coefficients vary greatly. Yeah? So if you can measure an uptake of 0.1 in the lab, and then in the atmosphere with humidity, it decreases by 4 orders of magnitude. But the point is, the chemistry models, you know, it's computational and an issue. And therefore, for let's say back of the envelope estimates, you take instantaneous. Now, in some cases, instantaneous is okay. It depends on the Henry's law constant. It depends on the species involved. I'm not saying it's always wrong, you know, but it depends how you want to extrapolate it, temperature, humidity, phase. You have to go in more details. Yeah. But that is not something we discovered. In principle, I think Stephen Schwartz, who came up with this resistor model end of the 80s, and it is in Seinfeld Pandey's book, it is all outlined there in principle. You know, we just go a little bit more into the details of this. Yeah.
Thank you. Omar?
Nice talk. So the glacier state depends on the humidity and the organic composition?
It depends on composition, humidity, and temperature.
So if we have particles main composed by hydrophobic organic compounds versus the hydrophilic organic compounds.
Do you want me to comment on that? Yes. No. I can say something. I cannot show that. I didn't show it because, but yes, you can have, for example, if you have a very hygroscopic, hydrophilic material, and it's glassy, and you increase the relative humidity, keep the temperature fixed. If it's very hygroscopic but glassy, then it starts chewing up the organic quicker, and it will deliquesce. So the hygroscopicity, you still need to know if you have hydrophobic or hydrophilic material. So some people, you will see that at conferences, they say, oh, the particle is glassy, so nothing will happen. That's not quite right. If it's hydrophilic, it can still deliquesce under atmospheric timescales. For that, we need to know the composition. So for example, we published a study looking at biogenic SOA. and for ice nucleation. And there was an SOA from longifolium, comes from trees, and it was glassy at room temperature. And I was so happy. I thought that was a missing biogenic IN. But it was so hygroscopic that as I increased the relative humidity, it just melted away before ice nucleation happened. So indeed, that's a good point. Therefore, we need to know the composition as well. So I can tell you if it's more hydrophobic or less hygroscopic, it will take longer to undergo this amorphous phase transition into the liquid phase. Whereas if it's more hygroscopic, likely, we have not much measurements on that, it will quicker deliquesce. Even at fixed temperature, just humidity.
Yep. Thank you.
Can I ask one question which goes right in that line? So you show us in the beginning that the particles are multi-component. So how about if we get like what Omar said, so we have one particle which is hydrophilic or hydrophobic and they are together and they might counteract each other, the effects. So how can we model this if the particles are multi-component and all the experiments you are doing are mostly single or two components?
No, that is exactly the challenge. So everyone who has right now high-resolution aerosol mass spectrometer, they try to resolve thousands of species and want to know what is the glass transition for each species. And the Nature Communications paper from Manabu Shiraiwa and co-workers, where they showed the physical state of SOA as a function of height. So they have compiled Max Planck now, I think 30 to 40,000 compounds or so, estimates. Many are estimates, there are some measurements, because the polymer and food industry knows about glass transition points. Has to do with food preservation. So if you're an expert in that, you get a job in the food industry, as a matter of fact. But there is some knowledge, but that is really the challenge. And we had one system where we used naphthalene and made SOA out of naphthalene. And the model would not get the glass transition point of the actual particles right, because the model doesn't know all the chemical products in the condensed phase. And so you see that many people, Neil Donahue, Shiraiwa and others, if they have high resolution data, that they try to really nail down the major components because they will affect the glass transition or the phase mostly. But it is, maybe it's not resolvable completely because you have millions of species, but this Nature Communication will give you a good summary in that, because they had exactly this problem. So they used all identified products from different SOA chamber experiments and put that in to predict the glass transition point as a function of humidity and temperature through the troposphere. And there are caveats, I would not bet my life on these data, obviously, but it shows you that is something which could be important.
Okay, thank you.
Nice talk, very nice information, and very nice photos about Mexico City particle matter. You know that Mexico City is a great region, and depends on the sun, the different activities had a great influence about the particle content. The photos that you present, in which part of Mexico City were obtained, the samples?
Oh, there was a T0 site in the Milagro study. That was center, but I don't know the exact district anymore. Oh, that's now embarrassing. I'm Mexico City. And we had the T0 site in the center, and then T1 further out, and then T2 towards the mountainous region, But I cannot tell you exactly anymore where the T0 site was.
¿Es el Instituto de Petróleo?
Enough part. Okay, please go on.
Thanks, I think this is very important because Mexico City have different activities, rural or urban side.
Yes.
Thank you very much.
No, absolutely, yes, and it gets then even more complex in a way. Yes, absolutely, I agree.
¿Alguna otra pregunta? Is there any other question? Omar?
So the glacial state depends also on the oxidants.
So I think Manabu Shiraiwa, and as he was still at Max Planck, they collected the data and plotted it as a function of the O to C ratio. And Thomas Koop, who put that first forward in a PCCP paper 2011, he plotted all the glass transition as a function of the O to C ratio. So the number of oxygens to carbons in the condensed phase. At that time they claimed it's not as strong correlation as, for example, molecular weight. But now people consider that too. Yes, and if you have more O2C, you may have higher oxidation, bigger molecules which condensed, and that could increase. And it goes into, it's not yet set in stone, but because it tracks oxidation, more oxidized may get its bigger molecules, heavier, it's more glassy.
So that means that we can obtain different SOA in Mexico City that, for example, in different regions with
fresh or aged, yes, yes, yes. So if you would have a bounced experiment from Sauco and you put it in a fresh area, you may get different bounce fraction than when they're more chemically aged. That would be
right. Beautiful, right?
Yeah, that would be beautiful.
¿Alguna otra pregunta? Okay, so I would like to ask the last question. So if I recall correctly, well, I read your 2010 paper a long time ago, so I might not remember the details. This is the paper that you got from Milagro, right? So
yes.
Here in Mexico City. And if I recall correctly, you said there that the ice nucleation activity was coming from SOA particles.
In a way, yeah.
Yeah, right? So that means that, so you show us today the complexity to study SOA particles. So if we as Mexicans, where I'm not Mexican, but I'm working here, if we want to understand our aerosol particles here, so should we jump into everything you are showing here? Because it seems like that SOA is a very important aerosol type here in Mexico City.
So that's a good question. So, I mean, it depends on your question. For example, if you say you study just the urban boundary layer where temperatures are high, you have a limited thermodynamic regime, and maybe you're in the more high humidity and higher temperature, and it trends more to the liquid-like state. If you want to study cloud formation, you go higher up, things change. So I would think for urban air quality, it's a tricky question. I was asked that before, and I think Neil Donohoe is always asked that, because in all his SOA formation models, they always assume it's liquid. But then Manabo and John Seinfeld, they showed, it could make it different in SOA yields in an urban scenario if there's just not even that they're glassy, just the diffusion coefficient just changed by 1 or 2 orders of magnitude. You don't need to be as liquid as water, but just a few orders of magnitude slower changes the formation mechanism. And so in that sense, I think maybe not to this extent. I just wanted to give you an idea and broad picture what it could all affect, but maybe a certain regime in the thermodynamics for mixing and growing, getting yield. And there John Seinfeld, I think, has a GRL paper which goes into that direction. And I think people are interested in that. Is just partitioning instantaneously, is that sufficient or not? And and there's quite an argument in the community right now. So not to this extent, but choose your phase, your phase diagram, and it could affect for SOA formation, but not orders of magnitude.
Okay. Okay, so thank you very much, Daniel. So please join me to thank you, Daniel, once more.
No, thank you.